Thank you very much for inviting me to give this talk. I think we were asked to introduce ourselves a little bit and talk about our interests, so I'll just spend 2 or 3 minutes doing that before going on to the main topic. I think many of you will know me already. My name is Matthew Foulkes, and I've been working at Imperial College for far too many years. I suppose I'm most known for using quantum Monte Carlo methods, which is partly about what this talk is about. But I've worked in all kinds of other things as well, including density functional theory and type binding, and a range of applications. The most recent ones, I've been working on warm dense matter. So that's matter that's so hot that KT is of order the Fermi energy. You probably already know there's a version of density functional theory originally formulated by David Mermin that works for those systems, or in principle does. But you may not know that until a couple of years ago, we didn't even have a reliable temperature-dependent LDA. So one of the things I did in the last few years working with Michael Bonitz in Germany was to parameterize a reliable LDA using quantum Monte Carlo simulations. I'm working on scale formation on alumina with Mike Finnis, for which I just missed a meeting because I was writing this talk. And I'm working on the dynamics of magnetism. So how, as atoms move around in a magnet, how do the spins move? In particular, if you apply very strong electromagnetic fields to the solid. So a wide range of interests, but what I'm talking about today is solving the many-electron Schrodinger equation with deep neural networks, which is just a work that I've been working on for about 2 years. And it started when I was approached by 3 guys from DeepMind, which is actually was founded by some academics from UCL, but was acquired by Google, and it's in King's Cross at the moment. And one of the 3 guys, James Spencer, is somebody I knew well because he used to work with me at Imperial. The other 2, David and Alex, were new to me. So David and Alex are physicists by training, and James is a quantum chemist. So actually, it's been really fun working with them. I have to say they've done all the work and had most of the ideas. All I've done is kind of nod sagely now and again, and tell them a little bit about quantum Monte Carlo that they may not have already known. So it's an interesting topic, I think. How do I get to the next page? Okay. So we, as condensed matter physicists or materials simulators or quantum chemists, are kind of lucky in that we have a grand unified theory already. It's the Schrodinger equation. And I at least believe that if we could only solve it, it would explain almost everything we encounter every day, probably even including biological processes. So in this equation, the DIs are nuclear positions and the RIs are electronic positions. The only issue is that we can't solve the equation. And in fact, there are papers saying that solving it is an NP-hard problem, which means that if we want to get exact solutions, we're almost certainly going to have an algorithm that scales exponentially with the system size. So the best we can really hope for are approximate algorithms that give you reasonably good results and scale like a power law. Going for exact results is hopeless. At least I believe it's hopeless. The other problem about the Schrodinger equation, and actually the fact that it's hopeless isn't surprising, because the Schrodinger equation describes so much of the world around us, it just couldn't have simple solutions. It's not, to me, surprising that it's a hard problem to solve. The other issue with it is that room temperature is 25 millivolts, KT is 25 millivolts, and the natural energy scale in the Schrodinger equation is the Hartree, the atomic unit of energy, which is 27 electron volts. And if you have a heavy atom, it could easily have hundreds of Hartrees as its ground state energy. So we need to solve the Schrodinger equation to extraordinary precision in order to get down to KT of 25 millivolts. In a sense, what this is telling us is that the Schrodinger equation isn't really a good starting point for us. It's too high an energy theory, and we ought to work with a lower energy effective theory, but we don't unfortunately have one at the moment. So chemists always talk about what they call chemical accuracy, which they regard as the minimum useful to do room temperature chemistry. And they say you need to be able to calculate differences in energy between different structures, for example, to 1 kilocalorie per mole, which in my language is 1.6 millihartrees per particle. So let's bear that in mind, because I'll talk about that a little bit later. So, of course, most people, including me, I love density functional theory and I use it. It throws away the many-particle Schrodinger equation and replaces it by an effective one-electron-like mean field theory, I know in principle it's exact, but in practice it relies on an approximate exchange correlation functional. And it can, in fact, sometimes achieve chemical accuracy if you choose the right functional, but it's hard to know which one to choose in advance. And it certainly by no means commonly achieves that accuracy. You can, of course, once you've narrowed down your problem to a very narrow range, you can tune your functionals and keep adjusting them until they get the right answer. But that always strikes me as a bit like force fields. It's perhaps not, you're not learning as much as you might hope you were. It still can be useful, of course, but that's a different question. So I'm trying to go a bit beyond density functional theory and see if I can find a generally more accurate approach. And the silliest approach you might imagine, there are lots I could have talked about, but I won't, is just to guess the many particle wave function. That does seem like an idiotic approach, but if you think about it, it was in fact responsible for most of the few successes we've had in understanding strongly correlated systems. BCS is, for example, it's not a Fermi liquid because the electrons pair up. That was a guessed wave function. Laughlin guessed the wave function for the fractional quantum Hall effect. There's the beta ansatz. There's quite a number of these guesses that have worked very well. They're mostly for model systems. And I'm interested in real materials, actually. And so you can also do wave function guessing for real materials. The simplest approach is Hartree-Fock. You just guess that the wave function is a determinant. You can guess a single particle basis and then construct a basis set of all the determinants you can build from that one particle basis. And that's the CI method that's useful in quantum chemistry, but scales exponentially with system size. I'll talk a little bit about Slater-Jastrow wave functions in a minute. Couple cluster, RVB states, Pfaffian's geminals, matrix product states, tensor product states. These are all kinds of guessed wave function. And you leave a lot of parameters in them, and then you try to optimize your guess by playing with parameters. And that's all very well, but suppose in this talk, I'll go up to systems of 30 electrons, although with this method, we can currently go up to about 60. But let's take 30 as a number. If we have 30 electronic three-dimensional positions, we've got a wave function that depends on 90 Cartesian coordinates plus 30 spin coordinates. And so even if you just want to evaluate the energy expectation value here, that requires doing a 90-dimensional integral and a spin sum. And 90-dimensional integrals are not hard. Not hard, they are hard. So, but the best way to do integrals of high dimensions is usually with a Monte Carlo method. So you take this integrand and you rewrite it as I've just done below. It's a direct algebra, there's nothing in there. And then you interpret psi trial squared as a probability density in your 90-dimensional space. And h psi trial over psi trial you interpret as a function of position. You can think of it like a score function. It's called the local energy. And then the idea is you sample points from psi trial of r squared, and that's the probability density, which you can do using the Metropolis algorithm. And every time you find a new point, you evaluate the local energy, and you average the samples you've taken of the local energy, and eventually that gives you a statistical estimate of the energy expectation value. And so this is the root of all Monte Carlo, variational Monte Carlo methods, which is the simplest kind of Monte Carlo. And all you now have to do is adjust your trial wave function, which presumably depends on a bunch of parameters, to minimize your energy expectation value. The simplest kind of trial wave function you can use is what's called a Slater-Jastrow wave function. And this is being used in the vast majority of Monte Carlo simulations of solids until very recently, where you have a determinant, and you know that's not good enough because that's just Hartree-Fock theory. So you multiply it by an exponential factor of a completely symmetric function, so that doesn't mess up the anti-symmetry. The very simplest case is just a sum of pair interactions. And so if two electrons I and j get close together, this function u rises in value, gets more positive, and you're suppressing the wave function. So you're allowing the wave function to build in some information about how electrons stay apart. But this is not a general ansatz. It relies on one determinant, and it works quite well in weakly correlated solids. It scales very nicely with system size, but it's not good enough to do quantum chemistry. It's not actually better than DFT, this approach in this simple way. You can, however, use wave functions like this as a starting point and then use what are called projector methods to get much closer to the ground state. The best of those is diffusion Monte Carlo. And for solids, that is consistently better than even the best DFT. So that's really the most accurate way we have of studying large blocks of solid, by which I mean, 1,000 electrons or something. Here's a simple example of a Monte Carlo simulation, just because I haven't had a picture yet. This was done a long time ago by a postdoc of mine called Marzian, and we were looking at what we called sine wave jellium, which is a uniform electron gas, to which we then applied a sinusoidal external potential, and that created then a sinusoidal charge density. So this ribbon up the middle is the charge density. We put one electron in a low density region of the ribbon, and because we have a true many-electron wave function, we can calculate correlation functions. And in this case, it's the exchange correlation hole. And this is the exchange correlation hole given by a Slater-Jastrow wave function. Because there are no electrons to dig out a hole of, practically, where the first electron is, the hole has to be dug out either side. And so the hole lives on the high density regions either side. It's a bit like an image charge. This is what the LDA would assume. It would say this electron was in a uniform electron gas of a low density. So even with simple things like this, you can get quite interesting results. Okay, but I've just said it's not chemically accurate. And what do you do when it doesn't work? So that was where we started off this work. And the first place we started was with the observation of the DeepMind guys, really. I must admit, I was really skeptical about neural networks until I started working on them. I'm now a convert. That artificial neural networks are flexible and efficient function approximators. So I'm not going to have time to explain them in detail, but that's really all they are. They are a computational architecture built mainly in software, but you can think of it as a hardware architecture if you want. You feed in a bunch of numbers at one end and out come a bunch of numbers at the other end. So in this case, we're feeding in electron positions in three-dimensional space and spins, and the number that comes out is the wave function. So our neural network is the wave function. We no longer have an explicit functional form. We have a neural network and all the parameters that define that network as our functional form. So this is what they were saying. Perhaps we can represent the wave function as a neural network. The second observation that I think was, I'm not sure who, it ought to have been due to me, but it wasn't. I think it might have been David who came up with it first. Nothing requires the orbitals in a Slater determinant, here's a Slater determinant, to be functions of a single variable, as they are in this one, and as they are in Hartree-Fock theory. The only requirement actually is that if you interchange the coordinates of any two electrons, I and j, you flip two columns of the Slater determinant, and therefore change the sign, and therefore you have an antisymmetric wave function. And so what that means is that you can actually do a much more general kind of thing that's not really a determinant anymore, where the functions inside it are still functions of one variable, but they're also functions, this is the set of all the other electron coordinates. And all you need to ensure antisymmetry is that the dependence of psi1, say, on the set of all other electron coordinates, in this case it's R2 to Rn, is completely symmetric. So if I flip R2 and R3 or R3 and R7, this psi1 doesn't change. And as long as that's true, for all of these orbitals in the determinant, these sort of many-electron orbitals, the determinant remains antisymmetric in the proper way, and the Pauli principle is true. So the main thing we've done in this work is to design a neural network, which we call FermiNet, which essentially builds functions, represents in a way these kind of functions that are functions of one variable, and then in a symmetric way, functions of all the others. So that's what this work is about. In case you don't know what a neural network is, I'll give you 1 minute on it before I go on to results. This is the simplest neural network you might imagine to evaluate a wave function of one particle. So on the input, we put in the XYZ coordinates of one particle, that's the green blob. We feed those into these blue blobs, which you can think of as neurons. They were modeled originally on neurons in the brain. You feed in essentially linear combinations of the inputs to each neuron. At the end of that first layer, this layer of neurons passes on all the inputs to the next layer. And what all these crossing arrows mean is actually a matrix multiplication. So you take the outputs of the first layer, you multiply by a matrix, and that gets you the inputs of the second layer. The layers don't have to have the same number of particles in, of nodes in. The matrices don't have to be square. And so what we've got so far is a sequence of linear transformations. But the output was then the wave function. That wouldn't be very interesting because that's just linear, and a sequence of linear transformations is just another linear transformation. So what you actually also do is you add essentially nonlinear filters. So it models the activation of a neuron. So as the the amount of input adds up into a neuron, it gradually switches on, and the output depends in a nonlinear way on the sum of the inputs. That's essentially all it is. This is what we actually had to do. I won't have time to explain much of it, but what we've got on, I want to just show you the top left-hand corner. You probably can't read it very well, but each of these yellow blobs represents the input coordinates associated with the one electron. So we have, for example, the spacing of that electron from all the nuclei, and also the modulus of the spacing of that electron from all the nuclei. So that's what I wrote down here. So we have one of those for each electron, and we also put in electron-electron spacings and the moduli of electron-electron spacings. And those are all the inputs. And then we essentially feed through the neural network in a way, and at every stage we feed in two-particle information, the information about interactions in such a way as to maintain this permutation invariance like that. And so eventually the functions that come out are general functions of this form at the bottom, the one we were after, the ones that are now going to go into our determinant. And the last step is just to evaluate a determinant. And so from that, I mean, that's a very rough and ready explanation. There's an archive preprint if you want to read about it in more detail. So otherwise, it's absolutely standard variational Monte Carlo. You sample points in your 3n-dimensional space. You evaluate your wave function, which depends, of course, on your current neural network. You use that wave function, that current neural network, to estimate the energy using variational Monte Carlo. And then you adjust the network parameters to lower the energy. And neural networks have wonderfully efficient methods of adjusting the parameters that define them using algorithmic differentiation and backpropagation to get very efficiently to the best neural network you can. So here's some results. This is a single determinant calculation. None of our results here with a neural network yet, well, at least with a Fermi net. But this teal line at the top is a conventional Slater-Jastrow calculation done well for various atoms in the first row of the periodic table. This blue line below is when we built a neural network to do exactly the same thing as a Slater-Jastrow calculation. So the only reason it's better than previous state of the art is because the neural network is a very flexible functional form, but we can slightly outperform Slater-Jastrow. This is something called Slater-Jastrow backflow wave function, which is closely related to what we're doing, but ours is a generalization of it in a sense. And again, we can build a neural network that does a slightly better Slater-Jastrow wave function. And this is a single Fermi net determinant. We're still not at chemical accuracy, which is the gray bar, but we can easily get there by using, say, well, all the calculations I'm going to show you from now on use 16 Fermi net determinants, and then we get to chemical accuracy reliably for these atoms. One of the interesting things about this neural net wave function, one of the problems with a lot of quantum chemical methods is that real wave functions have cusps in them. Think of the 1s orbital of a hydrogen atom, but also when electrons approach each other, there's a cusp downwards because they don't like to be together. And those cusps are very difficult to represent with smooth functions or with expansions of ordinary determinants. But we put in the modulus of the distance between electron positions and electron and nuclear positions. And those moduli also have cusps in. So we can build a wave function that is a smooth analytic function of the inputs, which has cusps in. And we don't tell it what the cusps should be, but it learns them. These results, this derivative of the logarithm of the wave function with respect to the electron position near a nucleus should be -2 in a helium atom, and the electron derivative should be 0.5, and it magically learns that, and it's all built in. So that's a big advantage over CI methods, which have trouble with cusps. Here's some atoms done with more determinants. This is 16. Our Fermi net results are the green ones, which are the best ones here. 0 is experiment. Most of the other data are a coupled cluster, which is what quantum chemists regard as the best method they have that will scale to larger systems. And then there's variation of Monte Carlo conventionally done, which is the green one, and diffusion Monte Carlo, which is the method that gets us the best results we can get for solids, bar perhaps one other Monte Carlo method slightly better. So we're consistently getting 99.7% of the correlation energy in these little atoms. We've also done a bunch of molecules going up to 30 electrons by cyclobutane on the right, starting at 4 electrons on the left. Fermi net is the yellow line at the bottom, which is better than any of the other methods we tried. These are all coupled cluster methods done in different ways, but they're all good calculations. They're the best we knew how to do. And we've done some molecules which chemists regard as quite difficult here, like ozone. And the other thing is that although the error is increasing with system size, this is not the error per electron, this is the total error. So really, to get the error per electron, you have to divide by n, and it's still increasing with system size, but quite slowly actually, which is optimistic. You know, if we're being optimistic, it may scale quite well to larger systems. This is another problem that most quantum chemistry methods have trouble with. It's bond breaking, so we're pulling apart a nitrogen dimer, and the top line is the total energy. The bottom line is errors in different methods relative to the best estimate you can get. And coupled cluster, which is quantum chemists' sort of workhorse for going to larger systems, is the blue one. It's known to have trouble with bond breaking. So it's a slightly unfair comparison. But again, our Fermi-Net results, which are the orangey ones, are beating it. The last example I wanted to show you was the H10 molecule. This is not a physical molecule, but it's interesting because it was the subject of a big survey paper recently where all the methods anyone knows to study quantum chemistry of molecules were applied to this thing pretty much. When you look on a coarse scale at the top, they all look as if they're getting exactly the right answer. It doesn't matter what they all are, they're the sort of state-of-the-art methods. When you zoom in on the errors alone, so this is all relative to the green data here, which is the one the people who wrote this paper regarded as the best. The green ribbon is their estimate of the error in the green results, so it's not exact, of course. And this is all the methods they tried, including auxiliary field Monte Carlo, which is probably the best of them, a variation of Monte Carlo method, various coupled cluster methods. And the only thing we've done to this graph is added our own line, which is the yellow one. So this is by far the simplest of the methods used, apart from the other variation of Monte Carlo method, and yet it's among the best. So I think simplicity is always a good thing for scaling and doing more interesting problems with. So I think that's also very promising. So positives about this approach. It's way better than any other kind of variation of Monte Carlo, any kind of trial wave function, if you want, applicable to real molecules with more than a couple of atoms. Way better. It's up there with the very best methods that have been in development for over 50 years, and we've only been at it for a year and a half. It rivals coupled cluster for equilibrium geometries where coupled cluster is supposed to be good, outperforms it when there's a strong multi-determinant nature. The Fermi-Net wave function we build can act as a trial function for other diffusion Monte Carlo and other projector methods, which will gain us further accuracy. And we've only just begun. These other methods have a 50-year start on us. So I think it's an extremely exciting beginning. Lots of questions though. How general is our wave function? So we have a piece of maths that tells us that one Fermi-Net determinant can represent any antisymmetric wave function. Unfortunately, it's not useful as a constructive piece of maths. It's just a very abstract thing. But if it's right, it means that possibly we don't need linear combinations of determinants. And whenever you have linear combinations of determinants, you have exponential scaling. At least in CI you do with system size. So if that's true, if we can really get away with just a few determinants, even in larger systems, as well, we don't know that yet, that would be great news. Limits to the accuracy, what is it that's stopping us getting better, since in principle we think one Fermi-Net determinant should do? Can we do solids? I'm sure we can, but at the moment we've only been able to scale to 60 electrons, mainly due to memory limitations actually. These networks have 700,000 parameters in, so it's quite a lot of memory. Are they size extensive? In other words, if I take a bunch of helium atoms well separated and double the number of them, does the energy double? So in the small systems we've looked at so far, the results do appear to be size extensive. We can rip atom molecules apart and get twice the atomic energy and things like that. But we haven't proven that that's true. And how does it scale with system size? So ordinary variation of Monte Carlo scales very well, but this is definitely worse. But it is definitely power law, but we don't really know how well it scales. So that's all I wanted to say. Thank you very much.
Thank you, Matthew. Does anybody have any questions?
Hi, I'm Leoma. Can I ask a question?
Yeah, sure.
Hi, I'm Leo. I have a question. So usually for this kind of neural network stuff, then you need to have the input and output data in order to train the network. But from what you said, it seems that you don't need any output wave function from any calculation, because what you're doing is you have some parameter in your neural network, and then you minimize these parameters, and in order to find the lowest value of the total energy. Am I correct? So you don't need any output.
No, you're exactly right. So we're not learning from data like most applications of deep learning are learning from data. We're learning from the variational principle. So the great thing about that is you never run out of inputs. So do you remember the what was it called, the Materials Genome Initiative in the US, which was essentially trying to learn all about materials largely from data? And a lot of the data wasn't good enough, or there wasn't enough of it, and the results were more limited than you might hope. One of the nice things about what I call it learning from equations, or learning from, in this case, the variational principle is our equation. We can carry on generating data using our current neural network and kind of in a bootstrapping way, improve it continuously. So yes, you're exactly right. This is not like a normal application of learning to recognize cats or anything. It's very different. But it's one of the advantages physicists have, that we often have minimization principles that we can use, and we know they're right. So I think it's actually a good thing.
Thank you, Leo, for your question. Anybody else have a question for Matthew?
I have a question.
Yeah.
It's Carla.
Hi, Carla.
When you show the behavior of the error for Fermi net in the molecules and atoms,
Yeah.
works. It looks very smooth and just increasing, while in the other methods it goes up and down. So
Yeah.
is there a reason for this, and is this reason suggesting any way to control it? And the other question I had is about cost. How much does it cost to do this calculation with this?
Yeah, okay. So the error one, yes, of course, I've noticed how smooth it is, and I like that, but I don't really know why. It's not conventionally true that with ordinary variation of Monte Carlo, you get nice, smoothly increasing errors. And I think this is a real strength, but I don't understand it. If we knew how it was increasing, if we knew whether it was increasing exponentially or quadratically or whatever it is, then you could, of course, extrapolate it away. But I'm afraid at the moment we don't have enough information to know that. So as far as I'm concerned, this is a lucky result, and I don't really know why it's so good. But it's something we see quite consistently. The other thing is about, was about the cost. So luckily, all the computing has been done at DeepMind, but they've told me what they use. So the funny thing about working with Google is they haven't even let me see the code yet. They're working on open sourcing it, which is the good news, and I think they're getting close now. But until it's open sourced, I haven't been able to see it, so I just have to believe them. But they use something like, a typical big calculation would be, I think maybe some of them here can correct me if necessary, but I think it's 8 GPUs for 8 hours or something like that. So it's hard, it's time consuming, but it's not as bad as you might think. And the other thing is we've made no attempt yet to optimize this, to for example, make our representation of the wave function efficient. Or it has all kinds of information in it that for example, couplings between parts of the system that are very far from each other that I don't think should be required. So we may be able to do better. But at the moment, it's quite a big calculation for one of these bicyclobutane molecules. One run will take us a day or something.
Hi, I have a question, if that's okay.
Yeah, George, yeah.
Yeah.
Sure.
Hi. Yeah. Thanks. Yeah. Really nice talk. Thanks for presenting. First of all, just in relation to Carla's question, I'd hazard a guess that, for instance, that big spike at ozone was due to a failure of the coupled cluster.
Oh yeah, no. I'm not
you
surprised that other methods fail, but
sure.
I'm quite surprised that we don't. Yeah. But,
yeah. Yeah. Well, I guess the kind of the modification of the orbitals is cleaning up a lot of those kind of errors from a single determinant representation.
But that's telling us it is cleaning up some of the multi-configurational aspects, which is what
absolutely.
we're hoping.
Yeah. But I had a slightly different question as well, which was sort of I've been sort of more following the developments in neural network kind of forms for the wave function in lattice models, and there's quite a debate about the specific architectures of the neural networks, and the kind of the standard paradigm in machine learning is that deeper is better than wider networks.
Yeah.
And I was just wondering, you know, obviously there are a whole zoo of different networks architecture that could be used in those things. I was wondering if there's any insight as to whether, you know, in terms of, you know, for a given number of parameters, is deeper or wider better when you're thinking about a number of hidden nodes, or does it not matter, or is this something that hasn't really been investigated?
So although I talked about deep neural networks, our neural networks are not in fact deep.
Right.
They're just 4 layers. And I don't think we've gone bigger than that. We have tried narrowing them. And I'm trying to remember the results. There was a gradual degradation in the results as we narrowed the layers, but it wasn't dramatic.
Okay, but 4 is still, you know, I'd still call 4
very deep.
It's not very deep, but I'd still call it deep.
I mean, there's quite a lot of parameters in each. You know, it's still 700,000 parameters. Let's put it that way.
Right.
To define the whole network. So it's quite a big calculation. So the answer is I don't think we really know. All we've done is these things, they call them ablation tests, where you throw away bits of the network and see what happens. And I don't remember anything very dramatic happening.
Okay, excellent, thanks.
Brilliant. Thank you. Excellent questions, excellent talk. We're just slightly over time, so if we could move on